Okay, in the last segment, we talked about how to calculate pH, and that pH is based on the kW of water, which is 1.0 times 10 to the minus 14, and from this we can derive pH equals negative log of the molar concentration of H+, POH equals negative log of the molar concentration of hydroxide, pH plus POH equals 14, and hydroxide concentration times H plus concentration is equal to 1.0 times 10 to the minus 14. And so you can do pretty much all pH problems as long as you know either H plus concentration or hydroxide concentration. So segment 9 begins with more of the same. If we have hydroxide, for example, sodium hydroxide, which will give us hydroxide, because we know that is soluble from the solubility table, we might ask a question such as, what is the hydroxide ion concentration when the pH is 3? Well, pH plus POH equals 14, and we're going to go to the 10th place as a matter of standard practice. So 14 minus 3 is equal to the POH, which is 11. Okay, POH is equal to the negative log of hydroxide ion concentration. So if we're looking for hydroxide ion concentration, we're going to say that 11.0 equals negative log of hydroxide. Move the negative over here. Negative 11 is equal to the log of the hydroxide concentration. And then remember, to algebraically get rid of log, we have to take the anti-log, which is 10 to the x. So 10 to the negative 11 is equal to the hydroxide ion concentration. Okay? What is the pH of 7.0 times 10 to the 5th molar carbonic acid solution? Well, carbonic acid is weak, which means that when it deprotonates, we don't know how much H plus we get because it is weak. And so for these, the pH of weak acids, we'll largely look at these in Biochem 208. However, I will include this for extra credit on your exam, or perhaps assess you in some alternate way. So I'm going to flip the page over and show you how we would do this. Okay, so let's say that we have a question like this. What is pH of 0.000010 molar acetic acid solution? Well, acetic acid, strong, weak, or buffer, it's weak, which means that when we deprotonate, double arrow, we don't know how much of this we get, and we don't know how much of that we get. However, since there is a double arrow, we can write a Ka expression. So Ka is going to equal to the molar concentration of H plus times the molar concentration of the base, which is acetate, divided by the amount of acetic acid that we start with. Now, we don't know the H plus and we don't know the acetate, but we do know that it's a 1-to-1 ratio, which means that if we create X of this, we get X of this. So Ka we're going to look up in the table, and the table is 1.8 times 10 to the minus 5th equals X times X divided by the amount of acetic acid that we start with, which is 1.0 times 10 to the minus 5th molar. Now we're making some assumptions here. We're going to ignore the 5% rule, and we're going to ignore what we call ice tables. because we don't want to have to futz around with the quadratic equation. But basic algebra tells us if we have one unknown, we can solve this equation. So 1.8 times 10 to the minus fifth, 1.0 times 10 to the minus fifth equals x squared, square root, x equals 1.8 EE minus 5 times 1 EE minus 5 equals square root 1, 2, 3, 4, 5, 6, 8.94 times 10 to the minus 6. I'm going to go to two significant figures. I'm not sure if you can see that. 1, 2, 3, 4, 5, 6. Okay, now remember that we are defining x as our H plus and our anion. So x is also equal to H plus. So pH equals negative log of H plus, which is negative log 8.9 times 10 to the minus 6. So I have my 8.9 times 10 to the minus 6, and I'm going to take the log of that, negative, and our pH is equal to 5.0. Okay, so the key here is that if you have a weak acid, you can't just plug into pH equals negative log of H plus, because you don't know what this is. So the only way you can do it is to make a couple of assumptions, write a Ka expression, solve for H plus, recognizing that H plus will be the same as the anion, whatever it is, divided by the amount of acid that you start with. Solve it algebraically, take that number, plug in negative log, and that's how you get the pH. Okay, back to the task at hand. We would have to find a Ka for carbonic acid, H plus, HCO3 minus, divided by the amount of carbonic acid that we started with. Okay, now I believe that the Ka is 4.4 times 10 to the minus 6. So we're going to go with that. Okay, and I'm going to put a question mark because I'm at home and I don't have a Ka table in front of me, but I think that's what it is. So if it's something different, well, cut me some slack a little bit on this and put in whatever it is. So just go along with the methodology on how we solve this. This is x. This is also x, because it's a 1-to-1 ratio. X squared divided by the amount that we started with, 7.0 times 10 to the minus fifth. This times this, 4.4 times 10 to the minus 6 times 7.0 times 10 to the minus fifth equals x squared. Take the square root. Okay, so let me get my calculator in there. Exponent minus 6 times 7EE minus 5 equals square root 1.76 times 10 to the minus 1, 2, 3, 4, 5. Okay, so x equals 1.76 times 10 to the minus fifth. 1, 2, 3, 4, 5. And remember, x is equal to our H plus. So pH equals negative log 1.76 times 10 to the minus fifth. Okay, so this is still in my display. I have a different calculator than I had on the other ones. So I'm just going to push log, and I'm going to push negative of what's in my display, and my pH is 4.8. Okay, so you can see with the weak acids we're doing a little bit better, getting closer to 7, which is neutral. 7.4 is physiological pH, but it's still not good enough. So we will come back to this idea of how do we do better when we come back to buffers.